Committee, and then Professor Cochran and Professor Michael Lynn from bioengineering first serving, and then Alex Dunn is coming right back here. So we really appreciate the contribution of their time and taking part. So it's a pleasure to introduce Jamin, and we tell you a little bit about his background and a little bit about the work, but not much because he's going to do a better job of that. So Jamin did his undergraduate work at ICE, the Korean Advanced Institute for Technology, a very famous place around the world, and an excellent institution. He earned his BS in chemical engineering. He then went on to do his MS at Seoul National University, again, a really first-class institution, world respected. But before that, he had kind of an interesting background. So because of his father's work, and I'd like to introduce his parents, who are back, as well as his wife, Amy, back as well.
Hi.
So before his professional education, Jamin lived in Korea, and then in Chile. So actually his middle school and high school years were in Santiago, Chile. His father went there for his job. And that was a very interesting experience for Jamin. So he went to an American school, an international school in Santiago, became very proficient in English, which has served him very well as in Spanish. And, I can't test him anyway. But he became very cosmopolitan, very international. And he also learned some things during that time. For example, he began playing basketball, and initially he wasn't so good, broke the bench, but he was determined to do better, and he did, and he ended up earning a medal at an international tournament by the end of his basketball career. So, there's a trend there that you're going to hear about. He also served in the Korean Army for 2 years, which was another aspect of this very varied and rich kind of education. At KAIST, he was president of the Student Entrepreneurial Society. That kindled an interest that was already there, which also carried over when he came here, where he TA'd for a course with Ricardo Levy and Howie Rosen in creating new ventures. And he kind of got the bug and was really interested in that for a while, but then as research maybe was doing a bit better in the lab, he realized that he really was still committed to a research career. Not that he wants someday to be an entrepreneur as well, but he's now looking for postdoctoral positions and will continue his scientific training in that. But throughout this time also, he was active in doing things that were sort of above and beyond. So in his undergraduate work, he did a research project that received an award, and it was looking at different materials for random access memory. So in his master's, he's moving slowly towards what he's going to talk about today. So he's studying about chemical engineering processes, process optimization. And he did a paper which was published in Renewable and Sustainable Energy Reviews about minimizing the cost of regional energy systems. And because of that, he came here with an interest in biofuels, and that's what he'll talk about today. But he also came with the Samsung Scholarship, which is really the end of another story, because at KAIST, when he first started, classes were very demanding, and he then really improved scholastically along that way. But then also when he applied for grad schools, first time, that wasn't so successful. So what he did is he stepped back and thought about, well, what is it that they're looking for? And he got 2 more publications. He won an international award, and he got a Samsung scholarship that then made his application look very attractive, and he was accepted to our program, and we're very glad that, I'm very glad that he was. So you'll see that same trend in this project. People have been looking for oxygen-tolerant hydrogenases for decades because it's really the linchpin that is absolutely required if we want to think about photosynthetic hydrogen production. The ability to use sunlight and water as a source of energy, as a fuel, as a chemical commodity as well. And in order to make that work, because photosynthesis generates oxygen, we just have to have an oxygen-tolerant hydrogenase. And the one that people want to use is an iron-iron hydrogenase. It's very sensitive to oxygen. And so that was a challenge that Jamin accepted when he came. And I think that's all I need to say. So it's been a pleasure having him in the group. I look forward to watching him develop as a scientist engineer when he leaves here. But I'm confident that it's going to be a very good story as it goes on. And with that, I'll turn it over to Jamin.
Thank you, Jim, for the very generous introduction. And thank you all for coming to my biggest event today. For the next 45 minutes or so, I would like to describe part of the research that I did at STEM. As the title suggests, I worked on engineering an enzyme called iron-iron hydrogenase for enhanced oxygen tolerance. The ultimate vision, as Jim said, is to use this engineered enzyme for biological hydrogen production. So why do we want to produce hydrogen biologically? Before we answer this question, let's first review the importance of hydrogen gas to the global economy. Hydrogen is a commodity chemical that is produced by more than 55 billion tons every year, which is about the corresponding market size is well above 55 billion US dollars, which makes hydrogen gas one of the commodity chemicals with the largest market sizes. Most of hydrogen is currently used for fertilizer synthesis, but a growing proportion is used as an energy source or fuel. This is evident in part in the literature, where, if you can see on the upper right side of the slide, a journal devoted to research on hydrogen energy has gained considerable importance over the past decade. It is also evident in the industry. Companies like Hyundai and Toyota have recently made vehicles that will run on hydrogen gas. So clearly, it is gaining importance. And what happens is that for up to date, about 94% of hydrogen that is being used is produced from fossil fuels through a process known as steam methane reforming, or simply SMR. SMR is done at large scale in facilities like the one shown in this slide. And it requires high temperature and pressure, and thus makes the process energy intensive. But more importantly, SMR co-generates a substantial amount of carbon dioxide while hydrogen is being produced. It is estimated that the mass of carbon dioxide emitted during SMR is roughly 9 times of the mass of hydrogen that's shown in this slide during the entire process. So Jim and other researchers believe that we can do a better job. And we're specifically interested in biological systems and believe that these systems can offer an alternative route for hydrogen production that can reduce carbon dioxide emission and also be economical. We're particularly interested in 2 production technologies, namely fermentative and photosynthetic. In the photosynthetic system, we want to use cyanobacteria cultures where the native photosystems can take sunlight and water to generate electrons, which is indicated by blue arrows in this slide. So these electrons in the native cell will flow through a series of redox proteins known as ferredoxin, abbreviated by FD in the slide, and ferredoxin NADPH reductase, or FNR. And these electrons will be stored in the form of NADPH for cellular metabolism. We want to engineer the cyanobacteria culture such that enzyme called hydrogenase, which is abbreviated by H2As in this slide, is expressed which can take electrons from ferroxide and combine them with protons for hydrogen generation. And this enzyme can catalyze hydrogen production at a very high efficiency. So for the fermentative technology as well, we want to keep the same set of redox proteins and hydrogenases to catalyze hydrogen production, but instead we want to extract electrons from glucose through a series of biochemical reactions that is shown in this one. So if you can recall, the two technologies both use hydrogenases to catalyze hydrogen production as shown in this slide. And among various hydrogenases that are discovered in nature, we are particularly interested in using an iron-iron hydrogenase 1 from clostridium pastörianum, which I'll refer to as CP1 for the rest of the talk today. As you can see, the crystal structure of CP1 has been reported in 1998 by using X-ray diffraction measurements. And this structure allows us to better understand the molecular mechanisms that are responsible for the functional property of the enzyme. So as I said, CP1 is an iron-iron hydrogenase. And this classification is based on the two iron atoms on the right side that constitute part of the active site where hydrogen production is being catalyzed. You can see that this active site also has a 4-iron first circle cluster bridged to the 2-iron subcluster. And in fact, if you see the rest of the protein body of CP1, there are 5 iron sulfur clusters that are responsible for electron relay to the active site where catalysis happens. CP1 is about 6 nanometers wide in size for your reference, and the molecular weight is about 65 kilodaltons. But what is so special about this enzyme is that it can catalyze hydrogen production at an extremely high efficiency. We have measured the turnover number of this reaction to be as high as 1,500 per second per molecule at room temperature and pressure at a physiological pH of 7. And for your reference, industrially relevant catalysts have the turnover number in the order of 1 to 10 per second. So clearly, CP1 is an extremely useful catalyst to produce hydrogen. Unfortunately, it also comes with limitations. CP1 and all other known iron-iron hydrogenases are extremely sensitive to oxygen gas. In other words, these enzymes will become irreversibly inactivated by oxygen molecules. And in this slide, I'm showing a graph to let you know how sensitive this enzyme is to oxygen. And the data have been collected by a method that we have recently developed, which I'll further explain in the later part of the slide. But what you see here is that the y-axis of the graph shown in this slide represents the active CP1 concentration in solution. And the x-axis refers to the amount of time CP1 has been exposed to 5% oxygen. What you clearly see here is that the active CP1 concentration, starting with roughly 11 nanomolar, decreases rapidly over the course of half an hour. And you can see that it decreases in an exponential decay manner, if we analyze the inactivation rate constant, this decay happens with a half-life of 7 minutes. What the 7 minutes means is that the active CP1 concentration will decrease by half. Every 7 minutes, it is exposed to 5% oxygen. So clearly, this makes CP1 not useful for biological hydrogen production, because even if it can catalyze hydrogen production at a higher rate, the enzyme will lose activity in the kinetics that we'll describe further. So to sustain hydrogen production with iron-iron hydrogenase or CP1, researchers in Source Lab and other labs have worked to solve this problem by various approaches. But to our knowledge, none have succeeded. But they did generate significant insights that were helping us to better design mutants of CP1. And recently what we found was that we found a mutant named CP1X in this slide with a 3-fold improvement in half-life in the presence of 5% oxygen. And what this enabled us to do is that when we use this mutant for biological hydrogen production with either fermentated or photosynthetic hydrogen production system, we were able to improve the hydrogen yield in the presence of 5% oxygen over an hour by 4-fold. And this improvement in aerobic hydrogen yield with an iron-iron hydrogenase is first in literature, which Jim and I are very proud of. We have actually filed a full patent on the mutation that we discovered throughout the work with engineering CPU1 for enhanced oxygen recovery. So for the rest of the talk, I would like to describe how our discovery was made possible. And you can see we worked on mainly 2 projects that allowed us to find the mutant with enhanced oxygen recovery. So in the first project, we developed a convenient, reliable assay with which we can measure oxygen sensitivity of CPU1 that allows us to screen a lot of mutants in a high throughput manner. So by using this assay method, in the second part, we evaluated specific mutants of CPU1 where selected residues were mutated. And by using the assay that has been developed in the first project, we evaluated their changes in oxygen levels. Our first project has been recently published in the Journal of Biological Chemistry, and I invite you to read the paper if you're interested in the details of our work. So going back to the beginning, I said that we're interested in studying oxygen sensitivity of CPU1 and iron hydrogenases so that they can be used for biological hydrogen purposes. To do that, what we need to do is we first need to be able to measure hydrogen production activity of the enzyme, like the one shown in here, where the catalysis is such that it takes 2 protons and electrons to produce 1 molecule of hydrogen. To measure this activity, we can either follow substrate consumption, in which case protons or electrons, as highlighted by the green color here, or we can also follow hydrogen formation using different methods. And in literature, there are well-established methods to either measure electron consumption in this reaction or measure hydrogen formulation. One can measure electron consumption using a method, using a system called electrochemical cell, where the electron consumption can be measured in the form of negative currents. And we can also follow hydrogen formation by using a method called gas, or by using an equipment called gas chromatography, which can directly measure how much hydrogen is produced. So once we can measure hydrogen activity by using one of those 2 systems that I just described, we can then evaluate oxygen sensitivity by introducing oxygen gas to the system and see how this activity is impacted. And for the past decade, researchers have mainly used the forward method, which is electrochemical cell-based method. We call it as a protein film voltammetry, whose schematic is shown in this slide. So if you can see the left side, there's a simple overview of how this method works. And what you see is that there are 3 electrodes submerged in a solution, which is a source of protons for hydrogen production. And when you start with the working electrode on the right side, you can see that by using a chemical modifier, hydrogen molecules are absorbed in the surface of the electrode, like the ones that are shown here. And within the proximity, the electrons can tunnel from the surface of the electrode to the active site of CPU1 for hydrogen production. This working electrode is connected to a reference electrode that they can change the potential to which these hydrogen molecules are exposed to, which can drive hydrogen production or consumption. And it is also connected to a counter electrode that can generate electrons and deliver it to the working electrode. So within this setup, as you measure currents or as you measure electron consumption, you can understand hydrogen's activity of catalyzed hydrogen production. While this system has been resourceful for the past decade, it also suffers from some limitations. For example, as you can see on the right side of this slide, one problem is that it is hard to control the orientation of the absorbed hydrogenous molecules on the surface of the electron. Although this is a simplification, with these differences in the orientation, there will be different tunnel distances for the electrons to be used for hydrogen production, and this can impact currents that are being measured within the whole system. There are other limitations as well with this protein film voltammetry technique, which I summarized in this slide. So as you can see, the protein film voltammetry method also suffers from fast oxygen reduction by the electrode surface. because of the negative reductive potential, the oxygen quickly becomes reduced, which makes it more difficult to estimate the exact oxygen concentration the hydrogen molecules are exposed to. There's also a problem that I just discussed, which is the variable absorption. And then there's another problem where, which was the main problem that we wanted to address, which is low throughput. As I can tell, is that when you work with this system, it takes roughly 3 hours for a researcher to evaluate oxygen sensitivity of one sample. So clearly, this method is not suitable for analyzing oxygen sensitivity of hundreds of units that we would like to evaluate for changes in oxygen quality. So to address this limitation, we have developed a solution-based assay, like the one shown on the right side, where we now have a higher throughput. And in terms of numbers, roughly for 3 hours, we can evaluate up to 20 samples in terms of their oxygen sensitivity or hydrogen production activity. And we use gas chromatography to directly measure hydrogen formation rather than electron consumption. Another important advantage is that in this system, there's much slower oxygen reduction, which means it's easier for us to estimate the exact oxygen concentrations enzymes are exposed to. And we have a more physiological system for delivering electrons to hydrogenates, which I'll better explain in the next slide. So in this slide, I'm showing how our experiments are conducted using two assays that we developed, which are described on the right part of the slide. So assay number one takes electrons from NADPH and uses FNR and ferredoxin to deliver electrons to the hydrogenates for subsequent hydrogen production, which is similar to how we want to use this hydrogenase enzyme when we want to incorporate for volatile hydrogen production system. So in this sense, it better mimics the physiological way of electron delivery to CPU. In the second assay, we're using a chemical releasing agent called dicyanide to get electrons to produce ferredoxin, which then will deliver electrons to hydrogenates for hydrogen production. So by using those two assays, we can evaluate oxygen sensitivity in magnitude I will show later. But for the procedural purposes, what happens is that we'll prepare these assays inside an anaerobic glove box because we don't want any oxygen to be present when we start the reaction. Inside the glove box, we'll have a reaction valve like as shown in the center of this slide. And we'll seal it so that when it's taken outside the anaerobic glove box, it will be safe from the oxygen diffusion from the outside of the current. We'll put it on top of a stir plate so that oxygen diffusion kinetics is enhanced so that we are measuring inactivation instead of gas transport. And finally, we use gas chromatography to directly measure how much hydrogen has been produced in these assays over the course of time. One thing to note is that we use fine needle syringes to introduce oxygen gas to the reaction to study how oxygen impacts hydrogenase's hydrogen production activity. So using this method with the first assay, we first analyze how oxygen impacts hydrogenase's hydrogen production activity as shown in this slide. What you see is that as we expected, in the absence of oxygen, which is represented by the black line on the right side, we have a constant rate of hydrogen production indicative of impact enzyme activity catalyzing hydrogen production. What we also see is that when we start introducing oxygen at t equals 10 minutes, the hydrogen production activity decreases. And what we also see is that higher oxygen concentrations are more deleterious in that hydrogen production activity ceases faster. For example, when we have 1% oxygen versus 121% oxygen in the system. So having this data in place, what we did next was, in the literature, people have studied oxygen kinetics, inactivation kinetics using a protein flow voltammetry technique, and they proposed a inactivation kinetics model, which is similar to the one that we showed this one. Basically, they were saying that the activity will decrease in an exponential decay manner. And so when we tried to analyze our data to see if it supports this model, we actually saw that our data doesn't agree with the model proposed in the literature. And this was particularly pronounced when you look at the t equals 10 minutes in this slide. And what you see is that So the y-axis represents the hydrogen activity of the enzyme within this assay, and the x-axis shows how much this assay has been exposed to 5% oxygen. If we were following the exponential decay model, these points would also be placed on this dotted line in this chart. But we see a significant difference at t equals 10 minutes. So Jim and I went back to see what was happening that made this thing inaccurate. And what we noticed is that if we remove the time point that is representative of the anaerobic hydrogen activity of the assay, so by removing the time points that were taken at with the assay before introducing oxygen at t equals 0, by removing those data points, we're now able to correctly fit our data points that would support a first order or exponential decay model in terms of how the hydrogenous activity is impaired in the presence of oxygen. So as this slide shows, by analyzing the changes in hydrogenous activity after introducing oxygen, we were able to see that the inactivation follows a first order kinetics with the inactivation rate constant, which we'll call as K inact O2, as summarized in the upper side of this slide. So why was this happening? And what does this mean? What we noticed is that we observed that in our assay, when we add oxygen to the system, there were two things actually happening, which I'll describe in this slide. So first, in the absence of oxygen, we are producing hydrogen from CP1 or hydrogenase by using electrons that are extracted from NADPase in a way that is shown in this slide. We were expecting or hypothesizing that when we add oxygen molecules to this assay, oxygen will not interfere with any of the reactants of this assay, but we will only inactivate CP1. But what we actually discovered is that that is not true, and in fact, by analyzing oxygen peaks from the GC measurements, we noticed that reduced ferredoxin can also consume oxygen or lose electrons to the oxygen. And what this means is that because oxygen, now the ferredoxin can lose part of the electrons to oxygen, the reduced ferredoxin concentration, which is the substrate concentration for CP1's activity, decreases, and that is also responsible for immediate drop in hydrogenase activity once oxygen is added. So we want to separate this phenomenon from the hydrogenase inactivation, and that is why we were able to fit an exponential decay model when we excluded the anaerobic hydrogen activity in our analysis. Because this was sort of a discovery that we didn't expect, which is oxygen consumption or reduction by ferredoxin, we looked in the literature, and what we found was one paper in 1974 that reported that closed period ferredoxins were actually capable of reducing oxygen. However, in our experiments, we were using senseless ferredoxin, and so we were confirming and reporting that ferredoxins that are different from closed period ferredoxins are also capable of reducing reducing oxygen by donating electrons. And the way how we confirmed that it was the reduced ferredoxin that was losing electrons to oxygen is as follows. As you can see in this slide, when we started with this first assay, we omitted each reactant at an increasing manner. And what we noticed is that when we had the full assay present, we were losing or consuming significant amount of oxygen over the course of 100 minutes. So this is a different time scale now. And what we noticed is that when we removed the hydrogenase enzyme, we're still consuming oxygen. And there's a negligible difference between the two bars. And then what happened is that as soon as we remove closed-period ferredoxin or liquid ferredoxin away from our system, we saw that there is negligible decrease in oxygen concentration over the course of 100 minutes. And this kept happening. And the way how we checked that this oxygen consumption is because of electron loss to oxygen was that when we removed all the upper part of the pathway so that ferredoxin doesn't have any electron to be received, so that the ferredoxin is oxidized, like the one shown here, we notice that there's negligible oxygen consumption over the course of 100 minutes. So again, this tells us that it is a reduced ferredoxin that is losing electrons to oxygen, and this is something that we want to engineer in the future projects, because this obviously causes the productivity of our system to be lower when we're trying to produce hydrogen with this process. So after the discovery, what we went next was, because we now have a first-order inactivation kinetics, we checked if this inactivation rate constant is independent of CPM concentration or ionized hydrogen's concentration in solution. In this slide, what you see is that we changed the hydrogen's concentration from 5 nanomolar to 100 nanomolar, 20-fold difference in hydrogen concentration in the assay, and then we followed how hydrogen's activity changes over the course of the exposure to 5% oxygen. Here, the y-axis is plotted as a load of the hydrogen's activity. So if we follow an exponential decay model, we'll expect a straight line like we see in this slide. And what you see here is that for the 20-fold difference in hydrogen's concentration, we get the same slope of this graph, which means the inactivation rate constant stays the same regardless of the hydrogen's concentration in this assay. This is a very convenient feature for our project in the later part, because we now don't have to calibrate hydrogen's concentration when we measure their oxygen sensitivity. And this helps us to evaluate large number of mutants in a high throughput manner. So that was all the work done with the first assay. What we did was we now chose the second assay, where CPN gets electrons from a powerful reducing source like diamond. And in this assay, we try to see what kind of inactivation kinetics we'll get in terms of hydrogen being impacted by 5% oxygen intensity. So in this slide, what I'm showing is that with this assay, like in the previous assay, there's a linear correlation between the CPN concentration in the assay versus how fast hydrogen is produced or hydrogenous activity in the absence of oxygen. And what you see is a linear correlation. What it means is that when we analyze samples after exposing them to oxygen, we can see how much active CP1 concentration is remaining in the buffer by analyzing how fast hydrogen is being produced, at least within this range that I'm showing you. So using that, what we did was we started with about roughly 11 nanomolar CP1 in the solution and exposed the sample to a different amount of time, 10 minutes, 20 minutes, or 30 minutes in the presence of 5% oxygen. We removed those oxygen and saw how much residual activity was remaining in our sample. And what you see is that the changes in active CP1 concentration due to exposure to oxygen again follows an exponential decay model like we learned with the first assay. And what's more important is that this decay constant, which is about 0.1 per minute, is exactly the same value as we obtained with the first assay. So by having those two assays comparing each other, we now know that we have a functionally reliable assay for measuring oxygen sensitivity of CP1 when it becomes reduced by its physiological reducing department or paradox. So that is the essence of what we developed in the first project, and I would like to explain what is significance of this. As you can see in this slide, we now have improved the throughput of our analysis. And as I said before, we can evaluate up to 20 samples over the course of 3 hours in terms of their oxygen sensitivity or how their hydrogen percentivity is impacted by oxygen. It also is convenient and in a sense when you compare it to protein fluid voltammetry, because you don't have to absorb those hydrogenous molecules on the surface of the electrode. What you need to do instead is you will prepare those reactions inside a block bottle within a solution and measure hydrogen production in the presence of oxygen by using gas curve and natural gas. So we have a convenient assay for measuring oxygen sensitivity. And what we also discovered is that we discovered that paradoxins that are not post-pure, so other paradoxins, can also lose electrons to oxygen and create reactive oxygen species like oxygen superradical or peroxide anion. And this is a discovery that is important to biological hydrogen production because our loss of electrons to oxygen will lower hydrogen production productivity of our systems too, but it is also important in a broader biological scope because reactive oxygen species is involved with a lot of different phenomena inside cells. So as I described before, we now have a functional assay to measure oxidation sensitivity of CP1. The next thing that we did was to evaluate different CP1 mutants for changes in oxidation tolerance. So in order to, before designing specific mutants of CP1 to evaluate their impact on oxidation tolerance, I first studied how oxidation can activate CP1. The molecular mechanisms are shown here in a simple way. And what you see on the left side of the slide is that in the absence of oxygen, the enzyme retains an intact active site, like the one shown in this slide, where there's 2 iron subcluster and a 4 iron first order cluster. And as soon as oxygen is introduced to the system, we see that the oxygen binds to a particular position in the active site. There is kinetics for this, and for the literature, we estimate that this happens in the time scale of seconds. And then once the oxygen is bound to the active site, what happens is that it will become reduced and become a reactive oxygen species. And through a series of reactions that are still being studied, it will degrade the active site such that the end product, you have only 4 iron per cluster in the protein body of CP1, and the rest will fall out of the enzyme, and thus the enzyme can metabolize energy production. And for this reaction, in the literature, the time scale of this degradation of the active site is in the order of minutes, which also is what we observed with our assay. So with those reactions, with those mechanisms of oxidation activation in place, what researchers first tried to do was they tried to improve oxidation tolerance of CP1 or other iron-iron hydrogenases by blocking or slowing down the division of oxygen molecules to the active site where the catalysis happens. And what you see on the left side of this slide is the research of molecular dynamic simulations. And what they show here is that the different colors in this left side is a research of oxygen diffusion pathway in each trial. And what they were claiming is that there are mainly 2 pathways within CP1 through which oxygen diffuses to or diffuses away from the active site. So now that these diffusion pathways are known, what researchers did was they tried to modify some of the amino acids that are surrounding this diffusion pathway. Like, for example, this alanine under diffusion pathway A. They replaced this residue with a higher amino acid with a higher hydrophobic residue, like from alanine to leucine. And so if this will have impact on oxygen diffusion and binding to the active site. Although they saw some improvement in oxygen binding, what they noticed is that the hydrogen production in the presence of oxygen was not improved at all. In our lab, we also had a student who tried to have a more sophisticated way of blocking oxygen diffusion to the active site, like the one shown in this slide, which I won't talk about details for our presentation. But he also observed minimal improvement in hydrogen production in the presence of oxygen. The previous attempts were unsuccessful, but just when I joined Storage Lab, what happened was that there was a group in Europe where they reported oxygen-tolerant nickel iron hydrogenase. So this is a different type of iron. This is a different type of hydrogenase that is good at hydrogen oxidation reaction. So splitting hydrogen back into proteins and electrons, but they're not good for hydrogen production, or their catalytic efficiency is very low. So we can still use these oxygen-tolerant nickel iron hydrogenases for hydrogen production, but nevertheless, they've discovered that these hydrogenases are oxygen-tolerant. And when they studied the crystal structure of this oxygen-tolerant nickel iron hydrogenases, like the one shown in this slide, what they noticed is that, so here's the active site of the enzyme, and here's a 4 iron first order cluster that is right next to the active site, which they call as the proximal iron circuit cluster. They noticed that the nickel iron hydrogenases that are oxygen tolerant have a different structure of the proximal iron circuit cluster that is shown on the right side. And what you can see here is that the ones that are oxygen intolerant have 4 iron 4 circuit as a part of the 4 iron 4 circuit cluster. But the tolerant one had the 4 iron 3 circuit, and there were extra 2 cysteines that were holding the cluster in place within the enzyme. There were further explanations on why this would make the enzyme oxygen tolerant, but the main takeaway for this defense is that this help the enzyme to become oxygen tolerance for some of the nickel iron hydroxide. And the source lab, before me, there was a student who also created a random mutant library, CP1. And when she analyzed oxygen tolerance of CP1 with an assay that measures hydrogen oxidation in the presence of oxygen, so not hydrogen production, but hydrogen consumption in the presence of oxygen, she discovered that the mutants that had improved oxygen tolerance while consuming hydrogen had mutations that were close to this proximal 4-iron first order cluster within CP1 in residues that are shown on the right side. So, but unfortunately, when she tested this mutant for hydrogen production in the presence of oxygen, there weren't any significant improvement. But these two research done before my work on this project really motivated me and made me think that maybe the amino acids that are surrounding these proximal clusters of the enzyme have a higher probability of impacting oxygen tolerance of the enzyme. And as you can see, what is true is that for CP1, it is a little bit different from the nickel iron hydrogenase that we just saw before, in that in this crystal structure with the iron sulfur clusters, there are two 4-iron first order clusters that are close to the active site. And by close, I mean like a regular electron column distance of 15 angstrom. What you see is that there's this 4-iron first order cluster that delivers electrons to the active site. Then there's a 4-iron first order cluster that is part of the active site. So I wanted to investigate how the residues for amino acids that are surrounding these two clusters impact oxygen tolerance. And for the naming purposes, because this cluster is not part of the active site, but it delivers electrons to the active site, we call it proximal delivery cluster. And the 4-iron first order cluster that is part of the active site, we call it as a proximate parallel cluster. And this is how this cluster is positioned within the crystal structure of CP1. And the diagram on the right side shows what are the specific residues that we chose to evaluate. These residues